Start. So hello everybody, I'm Stéphane Plassard and I'm teaching assistant of the TCP-IP course. And today I will do the lecture. So the lecture will be about TCP optimization on the IP multicast. So last week you have seen TCP, how TCP works. And we have seen that TCP puts a sequence number inside the packet and then sends the packet and waits for an acknowledgement. TCP is also a streaming services. It means that it sends the byte in the same order at which the application has delivered to the sender. So today we will see some what is called here bells and whistles. So this is TCP optimization. So TCP is an old protocol. It was invented in 1974, and there is a lot of improvement during this time. And all these improvements have led to a paper, and this paper are called RFC, Request for Comment. This is the official Internet architecture document, and you can see all this improvement inside this document. And so the question here is what we can improve. So the first question we can ask is, when should we send a packet? So the first idea we have is, first we write one byte in each packet, and we send each packet one after the other. This is what is done, for example, for an SSH interactive window. When you send a packet to the server, and the server echo back to your screen and give you the character you have typed on your keyboard. So this is the case for the SSH Windows application. But it is very efficient, because when you do that, there is a lot of overhead. For example, when you send a packet, you have a lot of header. You have the TCP header, you have the IP header, you have the MAC header, and all this stuff are around 60 to 80 bytes. And if you send only 1 byte of content, it is not very efficient, because you use a network, you use a lot of resources to create the socket, to send the socket, and all these things require a lot of resources. And so sending 1 byte of packet for 80 bytes of the size of the real size of the packet is not very efficient. So it is always a trade-off between the latency and the efficiency. When you send the packet, you have a latency. You want to improve the latency, but perhaps it's better to wait to have a better efficiency. So that's this case here. So perhaps TCP will be more clever if it waits before sending a packet. And it is what done the Nagel algorithm. Nagel algorithm will prevent to do many small packets. It will how it works. So first, it will create a packet with only 1 byte of information. It will send to the destination. But if it doesn't receive any acknowledgement, until of sending another packet of 1 byte, it will wait until having, for example, half of the maximum packet size. And so the idea here is to be more cautious, to wait before sending the second packet. Of course, if you receive an acknowledgement before, it means that the network is very quick, it's very fast, so there is no problem. So you can continue to do this work with a 1 byte packet. But the idea here is to prevent to do many small packets. So this is a Nagel algorithm. With the same idea, there is another question that are asked is, when should I send an acknowledgement? So we have seen, you have seen in the previous lecture that when you receive a packet, you send an acknowledgement. And the acknowledgement is inside the header of the packet. But in that case, the content of the packet is empty. So if the content of the packet is empty, it means you send an empty packet with just only an ACK without any information. So here you have also a lot of overhead due to the header of the packet. So the idea here is to, instead of sending an empty packet, you send a packet with some information. So you get a packet with an acknowledgement and some information. And then you can avoid to you can to have an efficient way to do. So another question we can ask is about the window size. So let me recall what is the window size. So the window size is reflects the availability buffer size at the destination. And it prevents the case where you have a destination buffer which is full. And if you send information to the buffer, as the buffer is full, at the destination, when you receive the packet, it will discard the packet because it cannot store the packet inside its buffer socket. So the idea behind here is to say, I need to warn the sender of the availability at the buffer at the buffer size of the destination. And unfortunately, there is one specific syndrome, which is called the silly window syndrome, which can happen. Let's assume that you have a busy server with a busy destination with a sender that sends 1 byte at a time. So when the buffer is busy, it means that the buffer socket is almost full. For example, let's assume that you have 1 free byte remaining in the buffer. In that case, the destination will send a Windows advertisement at 1 to warn the sender that there is only 1 byte free in the destination. So the sender will send 1 byte of information. When this packet will arrive at destination, it will fill the buffer destination, and then we need to come back, we need to send another window advertisement of 0 to stop the source, so that the source do not send any new packet. So you wait at the destination that the destination consumes 1 byte of data because you assume that the destination is very slow. And then when the destination has consumed 1 byte of data, as TCP says, you need to send another window advertisement on 1 byte to warn the application that you need to transfer new data. So it will send another packet of 1 byte. And you are stuck inside the loop with you will send an window advertisement 0, 1, 0, 1, 0. So to avoid this, you need to avoid this because this is a lot of resources that are wasted to do that. And here the idea is the same idea as the Nagel algorithm. The idea is to wait a bit before sending because you know that the destination is congested and make time to consume packet in the buffer size. And so you will wait a bit. Let's assume that the sender at 100 bytes to send, it will wait a bit. And when the destination consumes several bytes, it will send a packet of 5,000 bytes and the destination will consume it directly. So that's the idea, the thing you can improve inside the TCP, and the question you should ask to you if you want to improve TCP. Today, we will see 3 other improvements. The first one is how to detect packet loss. The second one is how to choose a specific sequence number, which is called SYN cookie, to avoid the SYN massive attack. And then the first thing we'll see is how to reduce the latency by avoiding to do a freeway uncheck. Before beginning with this 3 example, we will do a small poll. So here you have already seen this scenario before during the previous lecture. So you have several packets. So the time elapsed horizontally. You have several packets. Here 1, 2, 3, 4. And each packet are sent. The first one is acknowledged. So you will receive an acknowledge of 8,501. And then the packet 3 and packet 4 are lost. And the packet 5 is received as a destination. And so the destination will send an acknowledgement, the same acknowledgement as before, and with a SAC group, with a SAC block, which means that the packet 5 has already been received by the destination. And in that case, the question is, what should you do here? Do you resend the packet? The packet here is the packet 1 that we resend, or not? So I will open the poll. Poll is open. So I close the poll in a few seconds. So poll is closing. So you see that there is a majority that say B. And this is perhaps the rare quiz where there is no really good answer. There is because A and B are both possible. Indeed, it is the case. If, for example, packet 3 and packet 4 are really lost, you need to retransmit the packet. This is what TCP advises. You need to retransmit the packet, and this is the more the more good way to do. But perhaps, as the majority says, it's also already true. It may causes superfluous retransmission. Let's take the case where you will have reordering at the destination. You will have one packet which has a small delay. For example, a delay of 1 millisecond. So one of the two packets can arrive before the other. And so here, perhaps it's simply because the server is busy, has treated the packet 5, the packet 4, which is come before packet 3 and packet 2, and that has not yet processed these two packets. And an acknowledgement can happen just after in several seconds, and you have sent this packet for nothing. And then if you send the packet, hopefully there is no harm, because at the destination side, if this packet has already been received before, it will see the sequence number and see, okay, I already received this packet. I should not, I will not accept this packet because I already analyzed it before, and I discard the packet. Hopefully, it's better for TCP. Otherwise, it will be very complicated to use TCP. So the good response is A and B, and there is no good answer. And that's why we have fast retransmit has been introduced. So fast retransmit is an algorithm that is both that combine answer A and answer B. So the idea is when you have n duplicate of acknowledgement that are received, you declare a loss. So what is a duplicate? A duplicate corresponds, so here in this figure, we see the duplicate. A duplicate corresponds to a packet, an acknowledgement. We have the same value in terms of acknowledgement, but it has a SAC block with a gap between the ACK and the SAC. And so when you receive n duplicate, you declare a loss and you retransmit the packet. So for the previous example, if n equals 1, you will retransmit the packet. So here, n is most of the time equal to 3, which is the default value in the Linux system. And this is represented here with this graph. So here we have the time elapsed vertically this time, and we have several packets that are sent. So there are packet 1 and packet 2. The packet 1 and packet 2 are well received by the destination. And then you observe that there is an acknowledgement. There is an acknowledgement that are sent by the destination and received by the sender. So here it acknowledges 1,000, because remember that acknowledge means that it is all the bytes that are being acknowledged up to this value. On here, after, with the second packet, you have an acknowledgement of 2,000. So all these things until now. Here in P3, the packet is unfortunately lost. So as the packet is lost, the sender will not receive any acknowledgement. And then the sender continues to send packet P4, P5, and P6. For each packet, it will receive an acknowledgement. And this acknowledgement will be the same that the acknowledgement value will be the same as the acknowledgement value for packet P2. But this time, there is a SAC block where here it represents the packet, the acknowledgement for the packet 4. So it's 4,000. 5,000, this is the acknowledgement for the packet 5, and 6,000, this is the acknowledgement for the packet 5. And here you have 3 duplicates in a row. So with this simple algorithm for fast retransmit, you say, now I should retransmit the packet P3, and then P3 is retransmitted to the destination. This time it is good, it is well received, so it will send an acknowledgement of, so now 2,000, 3,000, the packet 3 has been acknowledged, and we know with the SAC block that packet 4, 5, and 6 has already been seen by the server, so it will send an acknowledgement of 6,000. So this is how it is on the internet to detect the loss. According to some Google sources, they say that most of the losses on the internet are detected using this algorithm of faster retransmit. However, this algorithm is an heuristic, and as all heuristic, there is some detections that are not detected by fast retransmit. Let's take the example of TCP connection. You send a lot of packets during the connection. Fast retransmit do the job, but at the end of the connection, it will send a packet, and this packet is lost. There is no more free acknowledgement that will be sent because this is the last packet of the TCP connection. And so fast retransmit will not recover this packet. So this is the same thing if you have an isolated packet. If you open a TCP connection, you send a packet, you close the TCP connection. In that case, the fast retransmit will not see the packet because there is no free more acknowledgement that will be followed by after the sending of the packet. This is the same thing also if you have some burst of loss. This happens, for example, if you have a line which is broken, and so every packet are lost, so there is no acknowledgement. So this is the same thing. We will have a problem in an issue in this case with fast retransmit. That's why TCP has introduced a timer, a retransmit timer. This is a timer that say at certain moment, so it's too long time, I did not receive any acknowledgement, you should resend a packet. This is something which is used as a safety in addition to fast retransmit. And that for every packet transmission, you will put a specific time stamp with a retransmit timer. And when one timer expires, it means that there is a big problem inside the network. And you need to do at scratch. You need to redo everything. All timers are reset, and all data is marked as needed retransmission. So you should say that, yes, why we do not use a timer every time, because it's simpler than using another solution. But sometimes it's difficult to have a good value of the timer, and fast retransmit is the best way to do that. So now we need to estimate. We need to estimate this retransmit timer. And this thing is very hard on the internet, because estimating the route trip time is something difficult. If you are in a constrained network, for example, you are in a communication network of a car, it's more simpler because you know exactly the distance between the thousands of computers that are inside the car, and you can compute the worst case bound on the route trip time among all these devices. It is, for example, in order of 20 microseconds. But on the internet, it's a bit different because first you have seen in the lab 0 that if your server is in Switzerland or if your server is in New Zealand, you have a factor 10 between the route trip time. Same thing if your server is busy. You send the request and your server is busy, so it will do a lot of things and we cannot send an acknowledgement. So there is a delay before it will send an acknowledgement. So the RTT will be very hard to estimate. And there is some algorithm that do that. Here we have an exponential filter that compute what we call the retransmit timeout, which is an estimate of the retransmit time, or the root read time. And as it is said here, it's a value larger than the root read time, but not too much to not retransmit the packet too late. So this is an exponential filter, and we compute it with this free value. So of course, we cannot keep in memory all the previous RTT because it's it's a lot of memory to keep. So we will keep only free value, the smooth RTT, which is a kind of average of the RTT, the variability of the RTT, which is an L1 error bound of the RTT. It is represented here, which is the absolute value of the difference between the smooth RTT and the last root read time measured. So this is the last measure of the root read time. And then the smooth root read time is a proportion between the last smooth root read time and the last measure root read time. And then you compute the retransmit timeout, which is equal to the smooth root read time, and take into account the variability of the root read time. And you see that there is a factor here, which is eta, and eta equals 4. It means that the retransmit timeout has a tendency of to do an exaggeration of the variability of the smooth root read time. So this is how it is done. So here we can see the evolution of the measurement of two things. So here you have in black the sample RTT, root read time, and in pink, the retransmit timeout. So the first thing you can see is here that the retransmit timeout begin at 6. This is a default value also in Linux. Yes?
Wasn't the timer implemented also in the first version of
There is a timer that is
the question is, wasn't also a timer in the first version of TCP? Why we're trying to implement another timer?
This is this timer which is done. This is this timer because before we use this timer which is computed as it is. This is a retransmit timeout, which is a timer which is used by TCP to determine these things. So this is the timer you speak about before.
Oh, okay.
This is the same timer. This is just before we don't explain how it works, but this is the timer which is used to determine how you detect a loss. But before we don't speak about fast retransmit, and here you build the two together.
Okay.
So yes, so you have the retransmit timeout here in pink on the graph, and it begins here at 6 seconds. This is a default value in Linux. And then you see that the exponential filter decreases quickly to the value of the sample RTT. This is due to the fact that the sample RTT has a few variability. And then you observe even here a plate between 40 to 60 around. Observe the plate where the retransmit timeout is exactly equal to the sample RTT. There you observe an increase of the sample RTT. And as I said before, as there is a variability of the sample RTT, the retransmit timeout will have the tendency to exaggerate this increase with this variability. And that's why it increases faster than the sample RTT. Here, when you have another plate, the retransmit timeout will decrease until there is a brutal decrease of the sample RTT. And even when you have a decrease, you will have an increase of the retransmit timeout because it takes into account the variability. So then you continue here, you observe this discontinuity, this important discontinuity here. And here you see that the sample RTT is constant for 110 to 141. And the retransmit timeout takes a long time before converging to the same value of the sample RTT. So two things to observe of this graph. The first thing is that here it's a sample RTT. So it means that sometimes the true RTT can be higher, And so you can retransmit a packet, even if it has not been lost. You can receive the acknowledgement just after, and you have received the packet. So this is also an heuristic, and so you can have some double retransmission, double transmission, and double reception. And then here you see that there is an important difference between the round trip time that can be observed. So here, let's imagine we have 1 second. So let's assume that most of the packets do have a round trip time of 1 second. And here the retransmit timeout is of around 10 seconds. So it means that if you lost a packet here, you need to wait 10 seconds to retransmit the packet. And during this time, it will have reordering and other stuff. So this is a problem, and that's why fast retransmit has been invented. Because here, if you use fast retransmit, during this time, it will, in 3 seconds, because there is several packets that arrive, in 3 seconds, it will resend the packet. Where here, it will wait a lot of many times. So that's the 2 key points of the graphs. So now let's begin with a small poll. So we have seen fast retransmit, and when do you think fast retransmit fail? I open the poll. I close the poll in a few seconds. So poll is closing. So we see that the majority says C, which is probably the good answer. So we will see why. So yes, of course, if you had at the end of the TCP connection, there is no more packet to send. So of course, you will have a packet that will not be seen by fast retransmit, as we have seen before. And in this case, hopefully, we have a retransmit timeout that will recover this packet. But as we have seen before, this retransmit timeout can take a very long time. There is 10 seconds versus 1 second. And so perhaps there is something which is behind, which is in the middle of the 2 solutions. So that's why a solution has been invented, which is called Taylor's probe. The idea of Taylor's probe is to have a specific another timer. We had several timers, but we have another timer, and this timer is called the probe timeout, PTO, which is equal to around 2 round trip time. And this time, when you have this probe timeout that expires, you will send a specific segment, which is called specific packet, which is called probe segment, and this packet will resend the data, the packet which has not been hacked previously. And so it will trigger a new hack, and might be also, it depends on the number of hacks which we will have received before, but it can also trigger fast retransmit. So this is a way to be more to have to have the packet retransmit quicker than with the retransmit timeout. I said probably for one thing is the solution D could be also correct. It may often fail due to packet reordering. So the idea behind that is the fact that you know that on the network there are a lot of different paths that can go to the same destination. And sometimes one packet can arrive quicker to the destination than the other. In this case, you will have a reordering that will happen. This is due to load balancing inside machine. So it can be avoided a bit with the per-flow load balancing option. If this option is enabled, if you have equal multipath, it means that you have two paths which have exactly the same cost. If you send a packet, we have with this option, per-flow load balancing, you will send only the TCP for one TCP connection, you will send the packet only on one path, or not on both paths. And this is a tendency on the internet. The tendency is to avoid to reorder packet at the destination. This is a tendency on the internet, and that's why they invent a new version which is called recent acknowledge, which is an alternative or a complement to fast retransmit. And in fact, recent acknowledge is a bit different than the previous version. It doesn't take a look on the number of acknowledgement or the sequence number. It will take a look on the timer. So let's imagine you have two packets that are sent very closely by the client. You receive the acknowledgement, an out of sequence acknowledgement, the acknowledgement of the second packet. If the time at which they are sent is very close, then the client will say, okay, they are very close, they are sending at the same time. Perhaps it may be due to reordering. But if the two packets are sent with a very different, an important time difference, then it means that the packets are not reordering. It must be, might be, because we are never sure, but it might be due to a loss. So you will resend the packet at this time. So that was proposed recent hack, and this time it based on retransmission time, on timing, and not on sequence number, because you will only see when the packet are sent, when you receive an out of sequence acknowledgement. So if this option is enabled, of course, the packet reordering must be the solution. The answer D could be the solution. So yes, there is a lot of improvements that are added at each time, and we will now see another improvement. So we have seen fast retransmit with the retransmit timeout, and now we will see another improvement of TCP, which is called SYN cookie. SYN cookie was invented now more than 10 years ago to answer to a specific attack that occurred 10 years ago. And this attack was as follows. You have a SYN server, SYN client. So you have a client on a server, and you have the SYN client that sends a lot of packets to the server, SYN packets. So he wants to do a TCP connection with the server. And to do that, he sends a SYN packet. So here it is written with an invalid source address, but some networks are smart and can detect invalid source address by doing reverse path checking. So this attack is also valid with valid source address. There is no restriction of this attack to invalid source address. So let's imagine you have a client that sends several SYN packets to a server with valid source address. So when the TCP server receives the SYN packet, it has a lot of things to do. First, it needs to open a TCP socket. It will reserve a lot of resources on the computer. It has to store some information, so the source IP address, the port number, also the source client address, the source IP address of the client, the port number of the client, also the maximum segment size. We will see after a while, and then store them inside the kernel space. So if you have only one connection, it's easy. But if you have several connections, it's a huge amount of work to do by the server. This scene needs to be stored inside the server until the socket buffer were created, has a timeout. So there is a timeout associated by the socket buffer, and when it time out, you can recover the space. But this timeout is large. It's necessarily large because let's imagine you are in the mountain and you want to connect to a specific to a server, and you have a very bad connection. You are over your cellular network and you would like to connect to a server. And when you send the first scene, it takes a long time to come to the server, and then the server sends you a scene hack. The scene hack, unfortunately, timeout. The timeout of the scene hack. It timeout, so you need to resend to do it again, and it can take a long time. So necessarily, on the server side, the socket buffer needs to remain open during a long time, for example, 10 seconds. But during this time, the malicious client that sends several scene packets, it can send, for example, 1,000 scene packets by second, and during this time, the server, the listen queue is full, and all the legitimate scene packets that would like to connect to the server will be dropped. So we have the server will be out. So that's why scene cookie has been invented. The goal of scene cookie is to avoid this attack. And in this case, we will see that it will not keep state information. At each time you receive a scene packet, the server needs to store information inside its own its local memory, and then you need to do all this work. Here, it will not store this information. Instead, it will authenticate the information it needs to remember and send back to the client. And when it needs this information to create the socket, it will recover it by asking to the client to give him this information. So let's see how it works on this small example. So here you have already seen this thing, which is the freeware uncheck. So you have a scene packet. The client is on left, server is on the right, and you have a scene packet which is sent by the client. As it is always done in TCP, the client will put a random number X, a random integer, which is the sequence number of the packet. Then the server receives this packet. In normal time, it will create a buffer. But here, it will create a buffer and send an acknowledgement. But here, it will be smarter. It will not remember all this information. It will use a cookie Y, which is here, which is Y. This is a state which is composed of several information. So this is a 32 bits integer, which is composed of T, which is a timestamp. This is the moment at which you receive the packet, and you do all these things. It's a way to check if, for example, a client would like to open a connection 1 hour later, it will time out and say this is too late. So this is a timestamp. Then you have the maximum segment size. So the maximum segment size is the useful part of the IP packet. Is the useful part of the IP packet. Here it is on 3 bits. It means that there is only 8 values that can be done. So it means that the server would like just to have a small packet, small information inside the packet. The maximum segment size is very used, and you will see it in further lecture on congestion control in 3 weeks, I think. It's very used to optimize the performance of the TCP network. So that's why it is important. And then this is the trick of scene cookie, is to use a cryptographic function that will compute a cryptographic hash. This hash will depend on several parameters. First, a secret key, which is known only by the server. This secret key is not client dependent. This is the secret key of the server. And it will hash this secret key, the timestamp, and all the value, client IP address, port number, the server IP address, and port number. And the idea here is this thing, if you do a cryptographic hash, nobody can recompute this hash if it doesn't have the secret server key. So here it chooses the while. It will put the trick of SYN cookie is before we choose a random sequence number, here we will choose a smart sequence number, which is the cookies, which is put as a sequence number. And here you acknowledge, this is the normal behavior of TCP, you acknowledge by taking the previous sequence number on increment of 1. Then the client will receive it. And if the client is a legitimate client that would like to do a true TCP connection, it will do as all clients do. It will send an acknowledgement. And this acknowledgement will be the previous sequence number, which is the cookies, plus 1. When the server receives this value, it can decrement it takes the acknowledgement, it decrement of 1, and now it has all the information to recompute the hash. It has its own secret key. It has the timestamp, which is inside the cookie. It has also the client IP address and port number by taking a look inside the header of the packet. And so it can recompute the cryptographic hash. And if the cryptographic hash is the same as this which is in the hack, it means that it is a legitimate client. And it will open do all the machinery, so create the buffer socket and store all the information. If this is a malicious client, the malicious client will float SYN packet, but after it needs to be able to convert all these source packet, and it needs much more power to do that. So it's not possible it's very difficult for the malicious client to do that. So here you have a penalty because on the server you need to compute this cryptographic hash, and this computation is long. Can be long because it requires some time computing. So the damage is now reduced to a time computing, but not on operating system resource which has unavailable. So you avoid that the server is out. So this is the better solution. So this is the global idea of SYN cookie. Now we move to a small poll. So here we assume that the server does not implement SYN cookie, which is most of the case, not 99% of the server implements SYN cookie because now there is a lot of attacks. So for example, if you would like to open a server at home, you open a port of your ADSL modem and you do a Wireshark, you will see a lot of attack on your computer, on your port. So you need to implement SYN cookie if you do that. But let's assume in this example, which is a theoretical example, let's assume that it does not implement SYN cookie. If the hack, you have the freeware on check, and here we assume that in free, the acknowledgement is lost. What happened? So I will open the poll. So poll is open. Okay. I will close the poll in a few seconds. So poll is closing. And the majority says C, which is the good answer. Yes, this time there is a good answer. So this is a good answer. So yes, we see that as the server does not implement SYN cookie, it will create a socket here, a socket which keeps the state information, and then it will send a SYN cookie. as the normal behavior of TCP is, when a packet is sent, it needs to resend the packet if it doesn't receive an acknowledgement. So it will send a SYN ACK. During this time, at the timeout of the SYN ACK packet, during this time, the keep state information of the socket is still open until the timeout of the socket. So the response C is the correct answer. The response C is the correct answer. But one more interesting thing is if the case when the server implements SYN cookie. So if the server implements SYN cookie, in that case, there is no socket buffer which is created on the server side after the SYN value, the SYN reception, because it forgets about the connection. And when it has sent a SYN ACK, it will not resend the SYN ACK because it has forget the connection. So if the acknowledgement is not received and if no information is sent, it will have nothing that happens. So we are faced with a deadlock. So hopefully some of the time, the client, which is here, do not send an acknowledgement with an empty message inside the packet. It will put a message. And if it is the case, it's a normal packet. And so the client will wait for an acknowledgement. And if no acknowledgement will come, it will send another time the acknowledgement with the packet, which is the packet that it wants to send to the server. But let's assume that you are faced with a situation where the client do the freeware uncheck and wait that the server send to him the information. Then you are stuck because the client waits the server send information, and the server do not know that the client will do this connection because it doesn't have received the ACK. So this happens for some application, for example, for SSH of MySQL. And in that case, you need to implement another timeout, which is used to resend the ACK to trigger the creation of the socket buffer. So this is a specific situation, and we see that when we bring a new method, we need to take into account all the counter size effect. So this is all for that one. We will perhaps make a break, and we will resume at 1:15. So we will restart with a small poll. So this time it's we enable SYN cookies, and the question is what is the response time of SYN ACK? So the response time is the time after receiving the SYN packet at destination on sending the SYN ACK packet. So this is the time to process information to the destination. So what do you think? So poll is open. What do you think about that? I will close the poll in a few seconds. So poll is closing. So the majority say A, which is the correct answer. So of course, with syncookie, you need to compute the cryptographic hash. On this time, it's a computation, it's a lot of time of computation. Of course, if you have a busy server, if you want to create a socket, as we have seen before, it can take also a lot of time. But this is also time to compute the cryptographic hash in this time. So this is more time consuming with syncookie than without syncookie. So this is the idea. And we have always a penalty to pay when we implement new things. Then now we have seen fast retransmit with retransmit timeout, first improvement. Second, we have seen syncookie. Now we will see TCP fast open. So TFO, TCP fast open, the goal of TFO is to avoid the latency, which is due to the freeway uncheck at the beginning when we open several connections. So let's assume you open a web browser, you go to Google or to Facebook, you begin a TCP connection, so you do a freeway uncheck with the server. Then you go to another website, and you come back few seconds or few minutes later, you come back to the Google or Facebook account. So you will do another TCP connection with another time you will have a freeway uncheck. So there is a latency, so the client is not happy. And the server also, because they would like that the client has the best service. So that's why TCP fast open has been invented. And the idea here is during the first TCP uncheck, where the freeway uncheck, the server will compute a specific tag, an authentication tag, which is compute. This is a hash also. This is a hash with a secret key, which is known only by the server, and the client IP address C. So this hash, this authentication tag, will be sent to the client by the server at the first connection, and then the client will store it. And at each time it would like to connect to the server, it will send this tag. So the client will send this tag. It sends this tag with the server, even with it can send also data. When the server receives this information, as it has the secret key on the client IP address, it finds this information inside the header of the packet. It can recompute the hash and check if the authentication tag T is the tag of a valid client that already have an interaction with him before. And then the server can send directly data in the first SYN-ACK packet. So instead of having a SYN-ACK packet which is empty, this time we put some data inside the packet in addition to the other information. And then with this method, the server has saved one route read time, because with the normal freeway uncheck, the server send data after SYN-ACK, and this is after the second route read time that it sends the data. So it saves latency on the server for the client. So this is a way also to authenticate the client, and it's quicker with this method. So now we have finished with all the improvement of TCP, to all the optimization of TCP. You have to take in mind that there are several other optimizations. I will give you only an intuition over three different ones, but there exist several, and some that exist in the past can be also modified now. This is the case, for example, for fast retransmit. I said that most Linux systems have wait for 3 duplicates before sending a packet. But as on the internet, we have a tendency to not avoid to reorder packet or to reorder packet over the internet. So this number tends to decrease and to go to 2, for example, before retransmit the data. So this is already this is always up to date, updated. So now we will see another thing. So the secure transport. So TCP was, as I said before, was invented in 1974. At the beginning, there was nobody that used the internet. They are only a researcher. They send packets between them, and there is no problem of security because they don't worry about that. But as soon as it became commercial, there are a lot of attackers that would like to take advantage of the non-security of TCP. That's why they needed to add something, another thing, which is a transport layer security. This is a security layer. This thing is not in the transport layer. It is above. It is in application layer. But I present it today because you never use TCP currently. You cannot use TCP without TLS. You can test it on your web browser. If you want to connect to a TCP connection without using TLS, most of the time, the web browser will refuse the connection, or will give you a warning by saying, are you sure you want to be connected to this website? This website is not sure. You can be faced with a man-in-the-middle attack. So that's why nowadays TCP is always used with TLS. So what does TLS? TLS adds two things to TCP. It adds encryption. Encryption means if you have two ends and someone wants to read the data in the middle, it cannot read the data because it cannot understand the data. The data is encrypted. And the second one is the authentication. The authentication prevents from a man-in-the-middle attack. If you have, for example, someone that would like you have authenticated the message and the destination. You know it comes from this destination. So this is the two things which are added to TCP with TLS. So now it's perhaps time to speak a bit about cryptography. Most of you know perhaps already all these things, but there exist two types of cryptography. There is symmetric and asymmetric. There are symmetric and asymmetric. The first one, symmetric cryptography, is the most widespread solution which is used. The most widespread algorithm is AES. And the idea is both parts will use the same secret key. So the sender and the receiver have the same secret key, and they encrypt and decrypt the message with this key. So this is a very efficient way to do. By efficiency, I mean that it is very quick to encrypt and decrypt the message. The time computation to do that is not very long. And so we can do use symmetric cryptography to authenticate a message and compute the tag, as we have seen previously. So we can use the same secret key, but we will see after that we can use two different keys, one for encryption and one for authentication. This is the same thing. So yes, here it's good, but because you can exchange a message securely. But the problem is when you want to exchange a message with me, you need before to have, when you want to exchange a message with me in a secure way, you need before to have something in common, a secret key in common. So it means that you need to find a way to exchange something before beginning the exchange. So it's a bit complicated. This is a problem, and that's why asymmetric cryptography has been invented. So the most widespread algorithm is called RSA, and the idea here, it uses two different keys. So each entity will have two keys, a key which is private and a key which is public. So the public key is accessible for every one of you, but the private key is just for one side of the communication. And so it's very difficult if you have just the public key. It's very difficult to compute the private key if you have the public key. So this is based on an algorithm for RSA, for example. This is based on an algorithm that factorize an integer into its prime number. So it's very difficult. And so the idea of the public and private key is the following. So let's imagine I have a message and I encode it with my private key. I will send this message to everybody. You will be able to decrypt this message. You will use your public key to decrypt the message. And then you will authenticate the fact that it's me that send you this message because I am the only owner of the private key associated to this public key. In the reverse situation, assume that I take the public key of someone in the room. I have a message, I encrypt with this public key, and I send this message to everyone. I know that only the owner of the private key will be able to decrypt the message. All the others will be unable to decrypt the message. So this is the idea of the private and public key association. So this is the problem of key distribution, but there is a drawback. This is very efficient, very good, but there is a drawback. It is time to compute these things. So to do the encryption and decryption, it can take a long time. For example, if I would like to compute a tag, which it can take around 10 to 20 milliseconds. So in all cases, you must be aware that the key must be enough long to not be decrypted. So in AES, in symmetric, this is 2056, and in asymmetric, it's 2000 bits. So now let's see how it works with TLS. So TLS use both system. It was asymmetric cryptography and also symmetric cryptography. So the first things that happen when you have here, you have Lisa that would like to discuss with the bank, and the bank begin to discuss with Lisa. So the bank sends what we call the certificate. It was a certificate. Inside the certificate, there is, for example, the public key of the bank. And when Lisa receives the certificate, the first thing she does, she verifies if the certificate is correct. Because it can be me that sends the certificate to Lisa because I want to store this information. And she needs to verify that this is the good sender of the public key. And how do she does that? She uses a specific public key, which is the certificate authority public key. This key is already pre-installed in your operating system or in your web browser. And you can verify that the public key is a correct public key. When you have done this checking, Lisa will create two session keys, one for encryption, L1, and one for authentication. And she will use the public key of the bank to encrypt these two values. And this gives a number Y she send to the bank. Then, as the bank is the only to have the private key associated to this public key, she can be able to decrypt Y and to recover the session key L1 and L2. And L1 and L2 will be now used to establish a symmetric cryptography, symmetric communication between Lisa and the bank. So at each time, L1 will be used to encrypt the message with using AES, and then you will authenticate the sender of the message by using the L2 key. So this key is using just during the session, and when the session expires, even if the session is very long, the key will be modified for security reasons. So that's how it works for two-way communication. There is an asymmetric encryption to determine the key, and then with this key, we do a symmetric encryption communication. So, of course, there is a penalty. As always, there is a penalty to do that. We have one more round-trip time. This round-trip time is due to TLS uncheck. At the beginning, all the client and the server agree on the cryptographic method they will use. So there is several things to agree, for example, the cipher suite and the cipher specification. All this stuff need to be agreed before because there is a lot of updates due to the fact that, for example, an attack can happen yesterday. And so you need to update all the cryptographic suite and all the cryptographic methods that are used. And that's why you need to have an up-to-date TLS software on your computer, and your operating system need to be up-to-date. Because if there is an attack before, you need to have the you don't have all cipher suites. Otherwise, it's not secure. So during this client hellos, there is also the server certificate, which is a public key of the server, and all these values are exchanged during the TLS uncheck. So after this TLS uncheck, they can exchange data. So how does it work in practice with TLS socket? So this is very close from the TCP socket, and you will be able to play with that during the lab 3. And the idea is as follows. So as before, the client will create a TCP socket. This time it is a bit different. It will add the security stuff it needs to have to add to build the SSL socket. So here it builds the SSL socket, and then you do a connection on a specific server for a specific port 5003. Then the freeware uncheck begins, so it's to open the TCP socket, and then you have the client hello, server hello for the TLS uncheck. On the other side, the server creates what we call the context. The context is all the set of the cryptographic material it needs to build a TLS socket. So there is a certificate, there is the public key and the private key. And then, as before with TCP, it creates the socket, bind to the socket, listen, it creates the listen queue, and then accept. It means that it consumes one SYN packet and connects the socket. Then it finishes the freeware uncheck. Here, into a TCP socket has been created, but the security material has not been added. That's why we need to do a WAP socket with the context we have created before. And then the TLS socket will answer to the client hello with a server hello. And then the discussion can begin between the client and the server until we close the connection. So it's very similar with the TCP, with what we have seen with TCP socket. So this is what I said. So now let's move to a small quiz. Poll. So I open the poll. So the question here is how many round trip time are required before data transfer can occur. So we have seen that TLS has an impact on the latency and the performance. And how many round trip time do TLS needs TLS? I will close the poll in a few seconds. So poll is closing, and the majority says B, which is probably the good answer, So here we will see why. So indeed, there is five messages that are sent. So there is one round trip time which is used for the TCP connection. So here we see SYN ACK, and then one RTT for establish the TLS session, client hello, server hello. So you have one read time here, one another read time here, and here we have an acknowledgement which is sent in parallel with the the root 3 tiles. So it's a bit more than 2, but this is around 2 RTT. So this is one of the problems of TCP. In TCP, we need TLS. This is required. And TCP plus TLS require a latency of 2 root 3 times, which is a problem because you need to wait a lot of time before sending packet. And there is one other solution that have been there is one other solution that you will see in the application lecture in 4 weeks, in the application lecture, which is called Quick. And the goal is to reduce this latency at the beginning of the connection. So now let's move to another quiz. So here we have a digital certificate that are being sent by the bank to Lisa. And this digital certificate is sent at the beginning of the connection. And then Lisa needs to verify this digital certificate. What do you think this digital certificate will contain? So I will open the poll. So poll is open. I will close the poll in a few seconds. So poll is closing, and the majority say D, which is the correct answer. So here the digital certificate is a certificate which is delivered by a certification authority and is given to the bank. This certification authority has its own private key. She will give to the bank the public key and the identity of the bank on the register du commerce. She will encrypt it with the private key of the certificate authority. And Lisa, have the certificate authority public key, so she can decrypt these things. Of course, Lisa does not, in the certificate, they are not the public key of the issuing certificate. Otherwise, it means that you provide a self-signed certificate. The bank will sign the public key with the public key of the issuing certificate. So it is not possible. It is as if you sign yourself your own thing for yourself. So this is not possible. So so response D is the correct answer. So yes, we need to be aware that if you install at the beginning, the certification authority public key are present inside your computer or inside your web browser, and you need to be aware that the original system installation was good and there is no breach of security. So yes. So that's all for today for TCP. That's all for today for TCP. There is another part on TCP performance and TCP optimization, TCP performance, but it's not something which is critical. So now we will move to another chapter. Yes. So yes, previously we was on the transport layer. Now we come back to the IP layer. And today we will see another topic, which is IP multicast. IP multicast. So you have already seen multicast address before because IPv6 uses a lot multicast address. And the idea of multicast is summarized on this slide. So this is an error message. So this is a French error message, but this is a message that you could have obtained several years ago if you were listening a French radio sender over the internet. And this French radio sender put this error message by saying that there are too many times you are connected to our services. It costs us a lot of money to maintain all these services and all these servers. That's why we have decided to disconnect you to this service. Sorry. Obviously, at this time, this radio sender will not use multicast, IP multicast, because the goal of IP multicast is to send the same content of information, the same stream of information to a lot of people, to a number of receivers. This is the case, for example, for IPTV, for example, football match. If you want to send news over the internet, live news, or it is the same also for financial information about the stock market or multiplayer game. And there is also some industrial applications that use multicast. And the goal is to send the information to 1 million of receivers, for example. So you can do as before, as you say before. There is a server that sends to a replication server and sends this information to all the destination. But the problem of that is if you have a replication server, you need to do 1 million. If you have 1 million clients, you need to do 1 million connections with each client. And for the server, it's a lot of job to do. So the idea of multicast is instead of doing that, perhaps it's clever to replicate the packet along the way such that each intermediate point will replicate the packet, but the server has less job to do. So the goal is to save resources on the server. So multicast is associated with a specific IP address. So we have seen unicast before. On unicast, IP unicast, you send to one destination. In multicast, it's different. You will send to a group of destinations, and you will have a specific multicast address. So this is the example here. You have one host that sends to a multicast group. The multicast IP address is 225.1.2.3. And there is several hosts here that will receive the same message. Only one message has been sent by the host, and all the receivers will receive the message. So the IP multicast addresses are of the form, of a specific form. They have the form 224 with a prefix mask of 4. So it means that the IPv4 address of multicast is between 224 and 239. And for IPv6 is FF00 with a prefix mask of 8. You have already seen this multicast address before. As I said just before, the example is in the Slack protocol. When you want to allocate IP link local address in IPv6, you will use the Slack protocol. And to do the Slack protocol, you need a specific multicast address, which is called the solicited node multicast address. And it allows you to give IPv6 link local address to the host in the same LAN. This is the same thing for the equivalent of address resolution protocol in IPv6, which is called neighbor discovering protocol. When you use this protocol, you will use the solicited node multicast address to discover the MAC address over the LAN, the local area network. For those who are more curious, you have seen also 224 address and PV4 multicast address inside the virtual machine for the lab. Indeed, we have when you do a Wireshark at the beginning, now you can do it, this is the same thing, you will see several UDP packets with a source address, which is 1.1.1 perhaps, but the 224, this is a multicast address. And this is normal because we have the server has been installed inside the VM such that you can play with multicast during the lab free, and you can see these packets that are sent every time in the VM, in the virtual machine. So you have already seen all these things before, but here we will go in detail on multicast. So there are two ways to do multicast. So multicast, of course, is used to identify a group. So there are two ways. There are any source multicast. Any source multicast is, means that you have a multicast address, and anybody can send to this multicast group. You just need to have the multicast address. So this is one way to do. There is another way, which is called source-specific multicast. In that case, the group is identified by the combination of your unicast address S and the multicast address M. So here, the source is explicitly identified. This is more in line, for example, by, as I said before, for video sender. You want to send a video to several hosts, you can use the source-specific multicast. So you can easily see if you are in the source-specific multicast mode or any source multicast mode by taking a look on the IPv4 or IPv6 IP address, because all the source-specific multicast address are on the and have this form. This is 232 with a prefix max of 8. On in IPv6, FF3 with a prefix fast on 96. So you can determine if it is source multicast which is used or source-specific multicast which is used or any source multicast. So now let's move to how it works. So the idea of multicast, so as I said, so here there is a simple network. We will show how works the exchange of data. And here it's a simple network. You have a source. This is, for example, the video sender. And you have several hosts, A, B. And you have a network of multicast router. At the beginning, nobody will join the group. So what will do the server? It will create an UDP packet. So yes, in multicast, you can only use UDP. Why? Because if you use TCP, TCP required an acknowledgement. So if you do 1 million connections in TCP, it means that you need to convert to 1 million to 1 million acknowledgement. So it defeats a bit the goal of multicast. That's why it is done with UDP. So S will create a UDP socket, and we send the packet to R5 to the multicast address. As there is nobody that learns that are subscribing to this group, unfortunately, when the router R5 sees the packet, it will discard it because nobody is listening on the group. So it's not very interesting, but the R5 will discard the packet. Let's assume that A now, the host A would like to join the group. So first, what is done is it needs to warn the router on which his link is on link with. You need to warn the router that he would like to join this group. So here we are in the specific case of source-specific multicast, but it works also with any source multicast. So here it will activate a specific protocol, which is called Internet Group Management Mode Protocol, EIGMP in IPv4, or MLD, Multicast Listener Discovery in IPv6. These two protocols are equivalent. And the goal of this protocol is to warn the router and would like to join, to subscribe to this particular group with unicast address S, source address, and with multicast address M. When the router receives this message, it will trigger a routing protocol. So this is what is written here. So there is a different way to do, but let's begin with the routing protocol. It will trigger a routing protocol. This is a discussion between router to establish what is the route to take to forward the packet. And here's the first thing that R1 will do. It will store inside the router the per flow state information. So here the per flow state information says, I have an host that would like to join the group SM. So if I receive a packet with destination SM, I need to route my packet to my left port. And then it will discuss with the other router, and will, with the multicast routing algorithm, R2 will have also this perflow information that say the perflow state information database, which is in the red rectangle here, will say, if I receive a packet from the multicast address, I need to transmit it to R1. And R5 do the same thing. It will update its multicast perflow state information database to send. If I have a packet to send to R2, I need to send to the south port. And then when a source would like to send to the multicast address, this time R5 will not discard the packet because it knows that it has something inside this red rectangle that says perflow state information database that says that I need to send it to R2. Same thing for R2 and same thing for R1. Yes, and then R1 send it to A, which the host which is on link with. So here it's so we see that there is a routing protocol that does the job. So there are several routing protocols, and we will see it in several slides, in further slides. So so here you have only one host that has joined the group, but let's assume that there is another host that would like to join the group. So B will do the same thing. It will use the protocol, which is called IGMP or MLD in IPv6, and with one the R4 router that it needs to join the group. R4 will store it in its perflow state information database, and then R4 will send a message to R2. R2 will store the information inside its database and will stop because it knows that it has already the information inside the router. So now, if a packet is sent by the source here, it will reach R5. As before, it will reach R2. Now R2 has two things to do. First, it needs to know that it has to duplicate the packet, and then it needs to send the packet. So there is one thing. Yes, so it duplicates the packet and sends the packet to the two hosts. And then A and B receives the information sent by the multicast group. So we have seen on this simple example that here you have one source that sends one packet, but you have a router in the middle that will duplicate the packet and send to two hosts. So you save on the server side, but the router is working more. Is it a good thing or bad thing to do that? So the router, in some sense, are real-time devices that are more fragile or more critical than the server. But the advantage of this way is, on the other hand, the advantage of this way is that if the source sends one packet, let's imagine you have 10 servers in a row, and the source sends one packet, and each server duplicates the packet. At each time, and you propagate it on a tree, but at each time, you will duplicate the packet, and at the end, you will have 2 to the power 10 packets, 2 to the power 10 hosts that will receive the information. But if the server needs to do that, it needs to send 1,000 packets and create 1,000 TCP connection, the UDP connection, sorry. So it's a lot of more works to do. So that's why it's better that the router do the job, and it's a small job for the router. Here it will just duplicate, whereas the server had to create 1,000 connections. So this is the idea behind the multicast. So there is two things which are important in multicast that you need to be aware. The first thing is this red rectangle, which is the perflow state information, which is different in multicast than in unicast. In unicast, you have a specific principle with the principle 1 and 2. If you remember, the principle 1 says there is one IP address for each device. So here, it's not the case with multicast. And the second one says that it is longest prefix match that counts. It means that you can, if you are a router, you can aggregate the address. And if you want to send to one direction in the table, you will have only a network direction, an aggregation of the direction, but not one line for each direction. Here, it is not the case because a multicast IP router does exact match for multicast group. So address cannot be aggregated with multicast. Furthermore, the multicast state information you have here is kept in the router for every known multicast group. And at each time, there is one host that would like to connect to the network, it will update this per flow state information. So it means that all the router on the path need to be, so here it's B, R4 and R2 need be updated at each time B send a request. So it's connect and disconnect and connect several times. At each time, you need to update the per flow state information database. So it is a dynamic table. Whereas when you remember for the routing table, it's not the case. It's something which is static. It changes only when there is one router which is removed from the network, or if, for example, a link is broken. But otherwise, this is a static table. Here we have a dynamic table. And this is one thing which is difficult with multicast. And we prevent multicast to be developed over the whole internet and over a large network, because you need to have this dynamic information on the aggregation. These two things leads to a scalability issue. So now we have seen all this per flow state information. And next week, you will see routing. We will see with the professor routing. So there will multicast routing and then beer, which is a sort of multicast routing. It's not exactly a multicast routing, but this sort of multicast routing. So I thank you for your attention. It was a real pleasure to do this presentation. I added a small Google form on Moodle to have some feedback about my teaching. So it will be cool if you give me a feedback about my teaching. And thank you very much again. And I wish you a good day and enjoy the lab.